What's up, everyone? Play a little bit more Microcorruption, I think. It's a little late, but need something to do tonight while I am stuck at home. Switch over to the webcam real quick while I log in. All right. We left off at Jakarta last time. This was a HSM1 model. And it had length checks. I think the big thing we saw was that the first one makes sure that we can read in I think it's up to 32 bytes. And the second get string will subtract off like from that. Blow this up a little bit. Maybe it's a little bit too big. I don't know. Do we need anything down here? I guess not. So the places we cared about were we see here, I think this is, yeah, so this is where it reads in up to 255 bytes. And then it immediately calls puts on it. So we're not working with the format string vulnerability here. We're just gonna have like a strictly a stack overflow, I think. So we probably don't care about this. This is where so this is the pointer, I think. Let's wait. Reset. That's what it is. Finish. We'll just continue. So 2401, this has a pointer in it. It's a 4638. For invalid password length. So that's interesting. So R15. I wonder if it's doing that because it's just going to cause the increment there. And it's going to hit the increment before it starts. So it's 2402. Ends up pointing to the beginning of our string. It must just be that. And so it's doing our test byte 0 of R15. It's looking for a 0 there. So not 0, it's going to jump back up to here and keep going along. Pop open a terminal. I'll always do that. once it gets through there, we're going to move R15, which is the end of the string, into R11. We can verify this just by clicking this, but so we see that R15. Oh no, we're not there yet. Continue. This points to 24OC. So 24. This is FED. FEDC. And so right here, this is the first null byte after our A's. And so this is the end of the string, and then we're going to subtract the 2402 from R11. In this case, R11 is going to hold what's on R15, which is the 24OC, and this just gives us the length of the string. And then what's in R14? R14 is 0. Okay, and so this is the stir copy that we get to, and so it's just copying it straight onto the stack. R14 is the address that the string starts at. And so it calls stir copy, and then we do we do a compare byte with R11, which holds the length with 32, and so it's running our stir copy before it does the length check. The problem is that if you look down here, we're going to go and, so we do this comparison, jump not carry to 45C0. So if it's less than that, it's not going to have to carry to do that operation. So it'll jump over it. But if it doesn't, then it ends up falling through here. It moves 2400, which is our beginning of it, which is this string, the 4638, which is this invalid thing, I think. 4638. Yeah, it's like right here, this invalid password length. Too long. So it fails, it ends up doing this, it moves it into there and calls puts, and then it does this branch to stop prog exec. And this is the problem, is even though we do this stir copy, and we can theoretically overwrite our return pointer here, we're never going to get a chance to return out because it's doing this unconditional branch, because it's going to fail this. We also know that the max size we can input is FF, and so FF is going to be not enough to overflow. The one thing we can look up is whether or not compare byte works on unsigned or signed values. It might be possible that if we get to like I forget what -1 is as a signed byte, but we can look up and see if maybe this is a signed operation, and FF would technically allow us, FF bytes would technically allow us to get into the negative space. So we can check this out. Oh, is it actually in here? We have compare but not compare byte. It doesn't say if it's signed or unsigned. the ones complement of the source operand plus 1. The two operands are not affected. The result is not stored. Only the status bits are affected. So it's interesting that it uses the ones complement. You know, we can just try it. One's complement. So we want one's complement, decimal value, -1. That's not helpful. -1. That's convert number of bits. Oh, 8 bits. One's complement. We're gonna do it by hand. Wikipedia, save me here. The ones complement of a binary number is defined as the value obtained by inverting all the bits in the binary representation of the number, swapping zeros for ones. The ones complement of the numbers behaves like the negative of the original number in some arithmetic operations, to within a constant of -1. Okay, so -1 ends up just being this, which is 254. Yeah, I know. I feel the same way. It's been since my organization class, and I always forget what one's complement is, which is the easier one, because the two's complement you have to invert it, and then you think you add one, or you flip the. Yeah, I think you add one for two's complement. So 254. So we can try this, and then theoretically this would be like -1 if it actually counts the amount. I mean, I guess we technically would want to do 8. So so we want 8. Or no, so we want 16 is 32 is the most we can do. So that would be 8. 8. 12. So 8, 16. 1, 2, 4, 8, 16, 32. So it would just be flip everything. And then what is that? That's 8, 9, 10, 11, 12, 8, 9, A, B, C, D. And that's F. So DF is 2, 2, 3. You end up finding anything about better COVID testing out by you? I've heard it's gotten a little bit worse out here, but it still is, like, I think pretty possible to get them. So let's try this again. We're gonna reset this and so I found out that my I had a false positive. Yeah, are you done for the rest of the year? I did my last day today. Yeah, so 2 weeks ago I tested positive on a rapid test, and I also took a PCR at the same time. The rapid test came back as positive. I asked the doctor, like, is it likely a false positive? He's like, no, it's almost never a false positive. The only way it's really a false positive is if, like, they screw up, like, doing the test. And so I just waited, and I never heard anything back about my my PCR. So I just assumed that, like, it was the same thing. And my partner never tested positive, and so I was confused. So I went back in. I got another rapid test, another PCR, and the rapid test came back negative. And I called back about my other PCR, and that one was negative. And then my PCR test came back with this most recent one, and that was negative. So at this point, I'm pretty sure it was just a false positive. I'm not sure, like, what happened, but apparently it's very rare, and I just happened to get, like, really unlucky there. Yeah, it is a relief. I'm happy that I don't have it. I was, I clearly didn't, like, my symptoms that I had, like, were really mild, and so, like, I was kind of relieved that, like, when I thought I had it, like, it wasn't bad, but it's nice to know that I just didn't have it at this point. That's pretty cool, though, that they shut down for the last 2 weeks and just, like, give it to everyone. I wish that we did that. I think we have, like, a pretty, like, reasonable PTO schedule. It's definitely not like one of the better ones I've had, but I think like as a new employee, you get like 15 days, and then we get like 6 floating holidays and like 6 like regular holidays that are like the federal holidays. But like that's pretty much it. Yeah, I remember, like, in the startup world, I mean, like, most places I worked at were all like unlimited PTO. You just, like, took what you wanted, and for the most part, like, we all shut down, like, at the end of the year, just because, like, none of our customers, like basically everyone was on call, but no one had, like, stuff they had to do. So if something broke, you had to, like, go and, like, fix it, but, like, no one expected you to, like, put in, like, full days or anything, like, during the last couple weeks. Yeah, I've taken almost no time off this year. I did a week, like, a few weeks ago, which is, like, the first, like, real, like, multi-day, like, vacation I took this year. But I ended up just taking PTO for the last 2 weeks and, like, being done with it. I was getting close to, like, maxing out my vacation, and I needed to start taking days. So let's see here. Basically, we want to go check and see if this comes up with, like, a 0 value. So we're going to single step and see where this ends up going. Yeah, so that didn't work. It doesn't look like it it ends up working. It's unfortunate. Yeah. So I'm still not quite sure exactly what the solution is here. Like we know that within the first one we can overwrite the stack pointer, but we know that if we do that, we're never going to get to the point where we return out. Oh yeah, and if so since I'm not sick, if you send me over details, I can run out this week and grab the stuff you were asking about. Should be able to run over there and pick it up. So we have the stir copy here. Cool. Yeah, just let me know. So I'll basically any day but Monday I can pretty much do. I wonder if it's even like I think we have to write something here. I don't think we can give it 0. But so this is the first stir copy right here, and then it does the jump over to this, so 45C0 right here. So this is our next jump, and this is where it loads in the print your password string. And R14 here should have the length of our string, and so it's gonna. Sorry, R11 has the length of our string. It's gonna move 1F into R14. Like maybe there's something we can do here. Come on, reset. R11 has the length of our string 4 in it, and we're gonna put 1F into R14. And then we're gonna sub R11, R14, R11 is 4, R14 is this. And I'm not sure why we're doing 1F here. Because that ends up being like 30? 31? What is 1F? It's 31, yeah. So I guess we expect there to be... Maybe we can enter like just nothing. And then it ends up being 31 minus 0. And this is why I think it might be like an underflow or something, or an overflow, is that we're doing the and it's anding the 1 bit on this on R14. Like if there's some way that we can trigger this to be a 1 rather than a 0, all of a sudden we're able to read it like as much as we want. I guess we could try sending in 0. do that. Continue. And like it's putting 1F directly in there, which so if I did 32, I think it's too many, but so well, that does work. So now our 14 is FFFFFF, and we can and it 1F. That might just be it. Oh shit! So we gotta figure. This is where we need to write to. Is 40 10 11 2 3 4 5. So 5 bytes. And then our it's 5 bytes, and then our pointer, which is going to be, where is the unlock function here? 4C44. Okay, so so we'll do this in hex. 1 2 3 4 C4. I'm not sure if that's the right number. One sec. I think we're gonna need more bytes, but I'm not sure yet. So let's continue. And then 41. Where's the pointer that we're writing to? It's gonna end up being 4 0 1 0 0 1 1 2. So it's 1 2 3 4. It is 4 bytes. So I fucked up. It is going to be that. So then we can step. We'll finish. We'll step. We're going to get down to here, basically. And basically, we just need to make sure that R15 isn't too many. Oh, it's gonna be though. Oh no, but we can overflow it. I think we just have to write a whole bunch extra after, because we can do like 65535 like bytes, and it will wrap back around to be like, I don't know, like less. So here we're gonna end up like fucking up. Yeah, so that's fine. So if we look at this, we end up doing Jakarta, username is gonna be probably this. This doesn't actually matter. Password is must checkbox. So I think this ends up being basically something like this. So we're gonna do B. We gotta do 42 times 4, followed by 4C44, followed by, I don't know, whatever. This is like 2 bytes plus 6. Whatever 223 minus 6 is. 42. I do print or this. Yeah. So let's see if this works. Oh, yeah, I don't need that. That's fine. We're gonna get to there. We don't care anymore. And then this is basically where we want to be. Continue. And then like this. Finish. Continue. All right. And yeah, I think we just did it. So that's, we got past the check we wanted to. It looks like we didn't end up doing the stir copy though. Let's figure out why that is. We can reset this. But that's progress. We're on the right track, I think. So that's fine. We're gonna hit that. And then I think I'm gonna switch that out to hex encoded just so that it's easier to type. All right. So we jump over this. Did it not do the stir copy though? There should be a whole bunch of B's. Why? Are we missing it? It's like it's not doing the stir copy. Huh. So we're not going to be able to do... Let's see here. Where is that? It's we can't do more than 32 bytes because of this check right here. That I'm pointing out right here. That's gonna fail. So what we're doing right now is correct, and we're getting past it. But I don't know why the stir copy is not getting called. Let's single step this a little bit further. And then also let's 41 times 32. And this will end up just being a little bit easier, so we don't have to we're gonna continue, and that goes into there. Continue, and finish. And so we're right there. Is it just not... Huh. Maybe it's just reading 0 bytes. And that's why it's not failing. R14 should have the number of bytes we can read. And R14 has 1F. So finish. And it's, I don't know where it's writing to, but so yeah, it just copied these in. We are writing, well, that's enough. Puts, finish. We get our B's, and then 2402. 2402 is the beginning of our string. stack pointer to R15. Into R15, which is what, 3F F2. Oh, this is like, we might need to do a different value and a different number of bytes. So no, so it's copying from 2402 to 412. That seems right. 412, which is right there, from 2402. Yeah, so all that looks good. And yeah, that all looks fine. We want to get to right there, basically. I want to get there. So we're going to continue. We made it. And R15 has FF in it. And this is the problem, I think, is that we're never getting past here. Yeah. Why did we think this was working before? So we can try doing less. Like we can just try doing, I don't know, like 10. Or we need to do more. It might just be we need to do a lot more. It's not going to be enough to overflow it, but let's see. Don't care about that anymore. Continue with that. Continue right here. Yeah, so we're definitely like way over. Oh, no, we're fine, because it's only comparing a byte. So as long as we push it over, we just needed to do one more before. We needed... In fact, we can just do this. As long as we don't go too far. Yeah, there we go. Paste that. Continue and continue. Yeah, so here we're over, but we're only 5 when it compares the byte. That worked. Sweet. Okay, so let's solve it. This is our username, and this is our password. Cool. All right, let's write this up real quick. Let's save the input. Theoretically, we could even pull 5 off of this. I think it would still work. So that'd be 18. I think that's technically like the minimum amount we can do. And have this like be 0, I believe. Yeah. So that's it. Where do it go? Did I lose? All right. This application similar to I think it's just like this, Johannesburg. Or like, you know, Santa Cruz. It reads in a username and password and uses stir copy to copy them onto the stack. It verifies the input length. And password combined are less than 33 chars, where the return address is saved 37 bytes down the stack. However, is an underflow when a couple things first. However, the stir copy check is made, which allows for the data to be written, be validated, And there is an integer underflow. That allows the password longer than originally intended 255 bytes. Of 205 bytes, which and is also an underflow that allows the password to be longer, maximum 2 bytes, when the username is exactly 32 bytes long. This allows the length to overflow past 255, which breaks the comparison check due to the fact that it only compares a byte rather than the full 16-bit value. Cool. All right. So I think we've now done all of the easy ones, maybe. This is 100 points. This is the first 100-point challenge that we're going to see. And I don't know what that means. Maybe we have to write more shellcode ourselves. So this lock contains the all-new Lockit Pro account manager. So this is all new. We're out of the HSMs, or maybe we have HSMs, but it does this other thing. The Lockit Pro D01 is the first of a new series of locks. It's controlled by Microcontroller 30 and is the most advanced MC, blah, blah, blah. The account manager solves the problem of sharing passwords when multiple users must have access to a lock. The account manager contains a mapping of users to pins, each of which is 4 digits. Each pin is 4 digits, I guess. The system supports hundreds of users, each configured with his or her own pin, without degrading the performance of the manager. There's no accounts set up on the Lockit Pro account manager by default, and administrator must first initialize the lock with the account and their pin. User accounts are by default not authorized for access, but can be authorized by attaching the account manager authorizer. This prevents users from adding themselves to the lock during use. Okay. I don't really know what that means yet, but I think we're going to figure that out. So far, this looks pretty much the same. There's heap exploitation, maybe. All right. We still get the unlock door function, which means that we're going to end up probably trying to call this or writing our own shellcode to do it. We get some mallocs. We get some frees. Maybe we can do a double free. My guess is that we're gonna have a heap corruption of some sort. That maybe we can get like a double free and do an overlap of space, which allows us to like write pins that don't exist or that other people's pins. Test password valid. Where does it start? So main calls login. I guess let's just run this. The CPU requested user input from the console. I thought we didn't have usernames. Passwords are between 8 and 16 characters. Am I in the wrong one? I'm so confused. So this is straight up ASCII right here. Like this, I think, is all ASCII. If we go to like 459A. Yeah. So enter username. These are all strings. So basically after ret here, this is all just like data. I don't know if this is meant to be confusing or if it's just like how it got like assembled together, but none of that matters. All of the code that actually lives in this test password valid, it is, let's see. So we move, what is R4? R4 is going to be the stack pointer, and then it increments it, and then decrements the stack pointer. So it goes up. So I think R4 is our base pointer. So R4 is our base pointer, and we're going to go 4 bytes up. So that's the first element on our stack from this. So we're going to move 0. So we're basically initializing a variable 0 that's going to be 0 on our stack. Then we're going to move FFFC into R14, and then add R4 to R14. That's fucking weird. 7D. 7D is not open. Is this an HSM? It is an HSM. Huh. Okay. Is that code still being used? I mean, this is basically just HSM1 code. Let's see. We do call test password valid. So it looks like we're allocating space on the heap. We probably want to look at what the malloc implementation does. So typically, when you have malloc, you're gonna have like some metadata, and the metadata is gonna have pointers to like, the next spot in the list. So we might be able to corrupt that and point the like the free value. So this is going to get freed, whatever is in R15 here. So one of those two strings it's allocating. If we can write the address of the stack pointer there, maybe we can cause it to write something in there. So let's see. We know that we get... What are we passing? We're passing 16. We're passing 16 here. So we're allocating 16 bytes. Let's set this. Continue. So R15 into R10. So R15 is going to be our pointer. So 240E. 240E. So F E. So this is the beginning of our user data. And if we look here, let's see, 24 1E, 8. So 0, 1, 2, 3, 4, 5, 6, 7, 8. So I think that this is like our heap metadata. And (24.0e). So without looking at like what the heap implementation actually does, it might be easier to look at free than at malloc. But basically we need to understand like what the heap metadata looks like so we can figure out what this data is. We're probably going to have a forward pointer and maybe a backwards pointer, but definitely a forwards pointer for the free list. I guess maybe it's worth diagramming this. I don't have a good tool to do that, unfortunately. But let's look at free and see if we can like quickly reverse engineer this. It looks not super wonderful, but yeah, this isn't too bad. So it pushes R11, so it saves that, and then it ends R15, which should have the size in it, I think. That's what we're passing it in, is R15? Yeah, it's R15. So basically we want to get, what is A? Is that just to get the A is what? It's 10. So it'd be 8, 0. Why would it and that? FA. So like, I understand why it's doing, so typically you'll see the 1 bit as like the in use bit, and so that's never really there. But I don't know why this is getting I guess they want everything except for this and this. but I don't really get why. FE. Oh, so it adds that to. Oh. Free should getting past a pointer. Why would it add that to R15? That's so bizarre. So this looks like it's the point where it's masking off the 1 bit because it doesn't care about that. Let's do this a little bit differently. The first thing I want to do is make sure that the heap is getting initialized. So main will call, it was just this, and it calls login. CTORs, and it branches to 4746. I don't know what 4746 is. Unexpected, okay. Clear VSS, decopy data. So that's fine. Let's look at what the heap looks like before all of this. Continue. All right. So two four zero eight. So 0, 1, 2, 3, 4, 5, 6, 7, 8. So this is probably a pointer to where it's going to start allocating from. Don't know what this is yet. And so we alloc. So these are all pointers to that same spot, 2408. This could be our wilderness. Or the size. 1FC8 is kind of big. That's like 8K. Is it exactly 8? That's not exactly 8K. If it's allocating 16 bytes. So typically, a malloc implementation is going to have a minimum chunk size, and the minimum chunk size is like gonna get rounded around like how much data you want. So if you want 16 bytes, it's gonna allocate you 16 bytes plus whatever it needs for its metadata. So let's see here. So 0, 1, 2, 3, 4, 5, 6, 7, 8. So it's pointing to itself. Usually that means that the free list is empty, I believe. We can continue and 1F9C. What's the difference there? That's 44 bytes. That's strange. So this is still pointing to itself. This is pointing to itself. And they're in use. 24, 3, 4. 1, 2, 3, 3, 4. 24, 1E. Okay. So this is pointing to here. And this is pointing to here. And this is pointing to itself. Which makes sense. So this is like a next pointer to the chunk right here. I wonder if it stores the data at the end. So like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So yeah. So basically, when we end up freeing it, it's gonna rewrite some of these pointers to point at the right things. What we may be able to do is overwrite like this pointer with the stack address, like where on the stack the return address is pointed to, and this with the value we want. And when it's gonna go, or when it frees, sorry, I think it's reversed. Maybe it's not. But when it goes to do it, it fixes up the addresses, and it will write the value we want to the place we want it. And I know this is kind of like confusing. I'm a little bit confused, but it all kind of clicks, and then it's really cool and it works. So these 21s right here, I'm pretty sure that this is the size of the chunk. So it's 32 bytes, and then the one here just signifies that it's in use. This is what I was saying, is like the last bit usually doesn't matter because everything increases by the larger number here. It always increases by like the minimum chunk size, which is maybe 16 bytes here. I don't know. So let's see here. Let's write some stuff. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Let's try BB. I don't know what was there before. Did anyone see that? Did anyone see if there was data there? Maybe we can redo this. Yeah. All right. So this is an address. This is what points to right here. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 1, 2. And that's fine. All right. And then we're going to read here up to what, 32 bytes. No, more. It's 16, 32, is it 48? So we're not going to call malloc again. So one of the things you could do is, because we can... I'm not sure exactly what this is. This might be a pointer to the free list. I think this is the heap size. Which is very big. So 4380. One F9C. Like, what does that put us at address wise? 23E4. It's within range. E4, E5, E6, E7, E8, E9, A. Oh no, I'd be in there. So I guess it wouldn't be, it'd be 24 plus 1 F9C. I mean, four, 3, 9. Huh. Yeah, either way. So now let's set the breakpoint there. We're going to continue. And we're also going to write here 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12, 13, 14, 15, 16, 17, 18. I'm going to wait on that. I want to go back so we can see. Yeah, this is the heap right here. basically we're going to overwrite this pointer right here, the 1E24. Yep, so we overwrote the 1E24. So we just fucked up some data here, and that's not good. This might be fucked up. I don't know yet. I think it's 08, but I'm not sure if that matters. So step, let's return out of this. It looks like we don't actually do any length checks. And so that's going to be important because we are overwriting like past like where we should. Oh, I didn't even see these like little boxes. That's cool. So we're gonna end up skipping over all this. It's gonna tell us that we're wrong, and we're gonna go to like right here, basically. Yep. All right. So then R11 is going into R15, and R11 is 24, 24. 24, 24. So that's going to be our second string. This is our password. So we're going to free this, and it's going to go back into the free list. So let's step, and it's going to call free, and then we're going to see some data change like maybe around here, definitely here. It might break. Step and then finish. So we saw this. This got changed from 2.1 to 2.0, and what that's denoting is that the chunk that we allocated here is now no longer in use. We want to go to 4.2.4.2, I think, or 4.4.4.4. Two. So it would have tried to update. Zero 24. So now this is back. And 006C. Oh yeah, so here we wrote our our 4242 right there. So I think we can just do this right now. Yeah, okay. This is all done in the username. So check this out. We need to find the address for main, because that's what we're going to end up returning. We got to find that on the stack. So basically, we're looking for a 4044 on the stack. Right here. All right, so it's going to be 9091 2 3 4 5 6 7 8 9 A. So 9A 43. So 9A 43. And it's going to be puts times 16. And then we need the address for unlock door. So it's 6445. I think this is it. I think this is our username. Continue. Save that, and we should see, yeah. And then finish. Continue. Just before one. Finish. Oh, the password has to be 8 characters long. Oh, it doesn't matter. This is our return point right here. 4564 and 439A. So we're gonna continue, and we're gonna step, finish. We have written 4564 and instruction unaligned 456A. Is that right? 456A? Oh, I did it backwards. I ended up writing data here. Try this one more time. Finish, continue. Just do 4-1. Finish. step, finish. We overwrote the wrong thing. 4, 5, 6, 4. 4, 5, 6, 0, 1, 2, 3, 4. 439A. It's 439A. 4, 5, 6, 439A. We're close. We have our arbitrary right, and like I can write data to where I want. I'm just not writing the right data to the right place. We were closer before. The problem here though was that we were writing. What we just did was wrote the address of the stack. I wonder if we All right, we're back. Sorry about that. We are we have an arbitrary write primitive. We can write right here. We're writing to the stack. The one thing I think we need to fix. So hold up, let's reset this. All right. And we'll finish that. And we're going to continue. And 41414141. Finish, continue. All right. So we end up doing our free, and that's going to end up writing right here. So step, finish, and we now have 4564. So 4564 is the function that we've now overwritten. But it's fine. I think if we're writing the A's here, we can just refill in the shellcode. So 4564. We have some zeros there. 4, 5, 6, 0, 1, 2, 3, 4. 1, 2, 3, 0. Three, 0, 2. Where is this coming from? We can get rid of these. We don't need them anymore. We might need to fix up something else here. Like some of the metadata is wrong, I think, which is the problem. It could be our chunk sizes where it's going the wrong. So typically the way that the heap metadata works is you'll have a size field and you'll have like a next pointer. So let's reset this real quick. We're just gonna do 1, 2, 3, 4, and continue. 1, 2, 3, 4. Oh, that's gonna look wrong. All right. So we see here we have our A's and our B's. So this is our user data. We should have 16 bytes here. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Usually our so this is our size right here. 241E. Yeah, so I'm not exactly sure what. So this is a size field, and this could be previous size. But it's probably the size field for this. Two, 4, 3, 4, 2, 4, 3, 0, 1, 2, 3, 4. 2, 4, 1E. Okay. So this is pointing to what's maybe the free list. Let's step through this. We're gonna step, finish. I don't know. I think my brain is a little toast right now. We have the right. We know what this is. We have a heap overflow or a heap corruption vulnerability. I'm just going to document this. Heap corruption vulnerability. 16 bytes are allocated to heap for both the username password and in bytes be read to corrupt the heap metadata and can turn an arbitrary write by overwriting the next pointer Yeah, I mean, I think we end up just having to slightly change this, but I mean, we have it. We have an arbitrary write. And at this point, it's just a matter of getting it to write the right data to the right place. Overwrite the return address of main on the stack with the address of unlocked door. I think tomorrow I'll be able to come back and get some more streaming in, hopefully finish up this challenge. I'll try to get a little more heads up. This kind of just turned into like a last minute kind of tonight thing. But yeah, it's been a good like almost 2 hours. We got through the one we were stuck on last time, and Jakarta, and we made progress on, I don't know, what is this one called? Algiers. Let's grab this. But yeah, I think that's it for tonight. My brain's a little fried, but like I said, tomorrow I think we'll be back, try to get through this. I think we're most of the way through the game. Check the profile. We can see Hall of Fame. I think we just go to the top and see. So there's 1, 2, 3, 4, 5, 6. There's 6 left. I'm hoping to get a bunch of streaming done in the next 2 weeks while I'm off work. I think we'll try to finish up the game and then probably get some other stuff done. We've got some red team tooling that we work on at work that we can try to get stuff going on Windows for, maybe build some additional features for it. That's all of this A-shirt stuff. This is the tool we've been building. We just open sourced it this year. But we've got some work here maybe we can do. And I am going to start working on rewriting the stack exploitation based course that I put together last year. I want to expand it and kind of get it into a state where I can offer it. It's specifically focused on AMD 64, so like all of our modern day like desktop and laptop computers, but it covers like basically like never touching assembly to going through and bypassing all the modern day controls. So kind of like what we're doing here, only different process or architecture and a lot more of controls you gotta bypass, like ASLR, stack canaries, and the like. So maybe we can get some work done on that and kind of stream like getting like the challenges built, the challenges solved, and some of the content around that. But anyway, have a good night, everyone. I hope you learned something, and I'll see you next time.